Hi, my name is Arya Niraula. I go to the University of Texas at Dallas, and my research topic is about identifying multiple security patches for complete vulnerability fixes. So before I begin, I'm going to introduce some key terms, starting off with CVE, which is a public ID for one specific software vulnerability, and NVD, which is the National Vulnerability Database, where it stores the official public record of CVEs and their reported fixes. A PDG slice, which is a program dependency graph slice, and that includes the specific lines of code a change actually affects or depends on. A security patch, which is a code change specifically intended to fix a vulnerability, not just a refactor or feature change. And finally, a GitHub commit, which is a single recorded change in a repository's history. So for more background onto these security patches, many software projects use security patches, which are shown in GitHub commits to fix vulnerabilities in their source code. But many vulnerabilities are fixed with multiple security patches, and some of those patches don't get reported to the NVD. And this is an example of a CVE ID that uses 3 security patches to completely fix it. So that leads us to our problem, where for some vulnerabilities, some of its patches are reported to NVD, but still have some important patches unreported. And our task to address this problem is, given a vulnerability, its NVD description, and one reported patch, we want to identify every additional commit needed to fully fix it by filtering out any refactoring, unrelated functional changes, and other vulnerabilities fixes from the commit history. And this is just an image that showcases that process. And for our scope of the problem solution, we focus on an LLM-based approach for identifying a complete set of security patches that can fully fix one vulnerability. Our input used for this LLM approach is vulnerability information, which includes the CVE ID and NVD description, one reported and verified patch, which is used as the hint commit and served as the anchor for the LLM to group other related and potential fixes to that CVE, and the commit history in the same version window as the reported patches for a particular CVE. And these serve as the candidate commits that the LLM would choose from. And based on those inputs, the LLM will give an output including a group of commits that fully fix a vulnerability together. And within that group of commits, there may be newly identified patches missing from the NVD report, and that is a case that we do target in this research. So the expectations of our results are that we expect to have accurate output for easy patch cases, which are defined by their simple structural similarity to the hint commit. And as this patch complexity increases, we expect that the precision may decrease as more false positives are introduced, and recall should stay more consistent than precision, but we expect that both should be reliably high for easy and PDG related cases. And a few studies that are related to this research topic include UTango, which is a GCN-based ML model that clusters code changes within a single tangled commit into concern-based groups using program dependency graphs and supervised agglomerative clustering. However, UTango only works within one commit. It doesn't link related changes spread across multiple commits, and it makes no distinction between security and non-security changes. And SPatch is a tool that uses fine-grained patch analysis and differential symbolic execution to identify safe patches and analyze functional impacts of code changes. However, UTango classifies individual patches in isolation as well, focusing on safe patch propagation. but it doesn't recover that multi-commit fix set. And dispatch is a patch decomposition system that aims to isolate individual security patches from entangled code changes. And even though dispatch does address security patches that are hidden amongst larger change sets, it focuses on one diff, not across multiple independent commits in a release window. It also doesn't use a LLM reasoning component as well. And SPI is a deep learning based framework to identify hidden security patches in open source software repositories. However, the large focus of SPI is to identify and separate security patches from non-security patches given a repository. It doesn't include analyzing patterns across different patches and grouping them together for one fixed vulnerability. And finally, Patch Finder is a hybrid ML and LLM based model that aims to identify the main security patch in a fixed commit for a particular CVE. But this model focuses on tracing down to one main patch for a vulnerability fix. It doesn't address the problem of multi-commit fix sets, and it also compares each commit to only the CVE description, whereas we compare each commit to the CVE description and a verified hint commit. So our design overview consists of a 3-stage pipeline where each stage builds upon the one before it. We first begin with data collection using NVD and GitHub API. Then we move on to stage 1, which addresses the structural similarity to the hint commit used for grouping together potential candidate commits that could help fix that vulnerability. Then we add on to that similarity stage with PDG slices using Jorn, and this stage adds that code dependency analysis aspect into the LLM's reasoning. And then finally, we move on to stage 3, where an LLM will double check each prediction made in stage 2 to see if it's valid or not. So more specifically, for stage 1, this is where the LLM directly compares each candidate commit against the hint commit and the CVE description using structural similarity of the commit diffs themselves. There is no code dependency analysis yet. It's largely just based on the commit diffs and the similarity amongst them. And an example of a case that is the most useful for this stage is figure 1, where it is an example of a CVE patch that has the same type of memset fix structure, and each patch also deals with a change to copy to user functions. So there is a very distinct pattern amongst all 3 of those patches there that is easy to identify and group together, making them fit into this category of easy patches. And other important similarity analysis that is added in this stage is the candidate commits files, functions, and subsystems that could also be touched by the hint commit as well. And if the candidate commit is part of the same patch series as the hint commit, and if the candidate commit addresses the same root cause described in the CVE description. Stage 2 adds on to stage 1 by addressing the problem that structural similarity alone can miss patches with complex or non-obvious code dependencies. And these code dependencies cannot just be modeled with only commit diffs. So this stage addresses that problem by adding PDG slices. And what this stage does is first we have the hint and candidates for each of those CVEs, and using those commit diffs, PyDriller is used to extract the before and after source code per commit. So the entire source code for each commit is extracted, then it's fed to Jorn to construct a CPG graph for each commit, And then we get the forward and backward slice extraction from that CPG graph. And then we feed all of those slices into the LLM and incorporate it into the LLM's prompt to add that code dependency analysis aspect for the LLM to reason with. And an example of a CVE or patches that this specific stage tackles is this CVE ID, where these two patches commit diffs alone can't show the complex dependency relationships between them, and outrightly they don't look very similar and can be hard to group together. So cases like these need these program dependency graphs to create a clearer picture and understand the entire similarity between those two commits. And finally, stage 3 is the validation process, where it addresses how stage 2's predicted groupings can include a large number of commits per CVE, and that leads to a lowered precision. And additionally, some of these predicted commits fix the same type of issue, but not the exact CVE as described. And validation works to clean that up. And its overall logic is that the LLM will look at each predicted commit's diff, slice, message, and files, and it compares its similarity to the hint commits fix and its relation to the CVE description to figure out if it's a valid commit that properly fixes that CVE as it's described, or if it's an invalid commit and it doesn't directly fix that CVE. And for our implementation and evaluation part of this research, we use GPT 5.4 Mini for the LLM implementation for stages 1 and 2 to analyze those vulnerabilities, commit history, and slices to identify additional patches. But for stage 4, we decided to change the model to GPT 5.6 Sol in order to recheck each prediction and get precise validation. And for code analysis, we use Jorn to generate those CPGs. And for evaluation of the LLM's results, we compared the results with the ground truth data, which includes the verified NVD records representing the multi-patch fixes for each CVE ID. And for the metrics for the evaluation, we use precision, recall, and F1, and they're all computed using the true positive count, which is the confirmed vulnerability fix present in the ground truth, and false positives, which is the unconfirmed vulnerability fix that is not present in the ground truth. And our dataset includes 77 CVs with multi-commit fixes curated from Linux and other related C and C++ projects, but we aim to grow towards 200 or more as the pipeline scales. And for our evaluation results, we compared each stage against a baseline value that did not use any similarity analysis or slices or validation for its reasoning. And overall, our implementation outperforms that baseline, where the macro F1 increases with each stage. However, stage 2 does have a decrease in precision, but it is largely due to an engineering addition we had to add into our code, where adding CPG slices in this stage 2 increased the input tokens per CVE, and there were 25 CVs that exceeded the context window. So we had to figure out a solution to mitigate that. And we decided to split the candidate commits into different chunks and then query the LLM chunk by chunk. And the effect of that was that the LLM returns a set of predictions per chunk, and then we aggregate those predictions together to form one group. And that results in more total predicted commits, and again, that results in the precision dropping. And after looking through the evaluation results, we found that our implementation does very good with cases where some predicted commits fix the same type of vulnerability as the CV, but not the actual CV as described. And this is because these commits have dependency relations that include non-obvious invalid commits. What that means is some commits may seem like they fix a CVE because they have the same type of vulnerability being fixed as a CVE, but they don't actually fix that specific CVE as it's described. And this is a case where that occurs, where patch 1 is the only patch that actually addresses the validation of the origin of NDP messages as the CVE here is described, because it correctly checks the IPv6 limit of NDP packets to reject non-local messages. So it has that criteria that validates those NDP messages. So it should belong to the CVE commits, and our implementation does mark it as valid. However, patches 2 and 3 do include changes to NDP-related functions and pointers, so they may appear to be related to the CVE fix, but they actually don't have changes to the NDP message validation, so they're not actually correct fixes for that CVE, and our implementation correctly marked both of those as invalid. Another example is this CVE, where it addresses an HTML injection vulnerability caused by improper decoding of escaped HTML entities during this conversion. And patch 1 is the only patch that actually addresses this vulnerability completely, because it adds this check and replaces any inputs that could be interpreted as potential code to prevent that HTML injection into the code. Whereas patch 2 does have CSS inlining updates, but it doesn't actually have anything that changes the vulnerable HTML escaping behavior. So it shouldn't belong to the CVE fix group, and our implementation correctly marks patch 1 as valid, but patch 2 as invalid. Now, our future work and refinements to this research focus on further scaling our work and increasing the 77 CVE count to 200 or more CVEs, and also applying all 3 stages of the pipeline to those CVEs, and examining more failure and success cases more in depth to determine the strength of the validation pipeline for larger code bases and commit windows. And that is the end of my research. Thank you for listening.